You will remember that we finished off with electric field. I think many of you wrote the test on the Wednesday before we wrote for Christmas. I have those all marked. I think many of you saw your test marked. There's one or two people that need to do some finish up on that, so I can't hand them back to you to keep just yet until they get returned. We spent Thursday and Friday, you remember, working on the Milliken oil drop research video. I will give you one more class. I've had a couple people asking if that's today. Normally, I don't do that simply because people aren't quite ready yet to do that and they don't have anything to do on that first day. So I will wait a day or two. Can we just schedule like Wednesday for the filming day, the last day? Is that okay? Give you another day to sort of get yourself together?
Yeah.
Okay? Or is Thursday better?
Thursday.
Thursday? Okay, Thursday's fine. So I'll schedule Thursday for, we're going to film on Thursday, Kurt. So if you want to take your camera home until Thursday, you can. Okay, so we'll do that Thursday. In the meantime, let's have a look ahead a little bit here and try to figure out where we're going. So, I believe I handed this to you already, am I right?
Yeah.
I did give you this outline?
Yeah.
Excellent, good. Okay, so this is what you're going to have to be able to do. To find the electric field qualitatively is a region of space around a charge where a positive test charge experiences force. That's coming in today's handout. Lucas, it's time to listen. We will diagram electric fields using lines of force with respect to a positive test charge. You'll have to be able to draw an electric field for me. Okay, it's very similar to a gravitational field. Okay, including single point charges, positive and negative, near to like charges, near to unlike charges. There's a variety of different ones. You will define the electric field quantitatively as a force per unit charge. That means kind of with a number. You should have this paper already. Did you get it? Not, you didn't get it today. You would have got it last week or the week before. I'm going to talk about E equals F over Q and solve problems using the unit field concept. We're going to get to that. We will solve problems for the motion of charges between parallel plates where there's a net force. This formula here is very similar to F net is equal to the applied force plus the friction force. Same idea. Okay, FE is electric force. You will describe a simplified version of Millikan's experiment for the determination of the elementary charge. That is the video that you are doing. Okay? And we can't really do this until you have a basic understanding of what's going on in Millikan. And you will define the elementary charge and convert between elementary charges and coulombs. Let's begin today by sort of doing an introductory little reading here. Okay? You may even get about maybe 20, 25 minutes today to do a little bit of Millikan research as well, because this should not take the whole period. Okay, so the handout that I've just given you, let's go to that there. And basically it just sort of is an introductory to electric fields and potential. The space around a strong magnet is different from how it would be if the magnet were not there. Put a paperclip in the space and you'll see the paperclip move. The space around the black hole is different from how it would be if the black hole were not there. Put yourself in that space, it'll be the last thing you do. Similarly, the space around a concentration of electric charge is different from how it would be if the charge were not there. If you walk by the charged dome of an electrostatic machine, like a Van de Graaff generator that you may have seen in grade 9 science, I don't know. Anyone get to play with that? The shocking thing?
Oh, yeah.
The big dome, yeah? I'm sure you did. Hair on your body stands out for some people, not so much on mine. Just a tiny bit if you're more than a meter away, and more if you're closer. The space that surrounds each of these things, the magnet, the black hole, and the electric charge is altered. The space is said to contain a force field. And so if you're a Star Trek or Star Wars or science fiction fan and you talk about force fields, it's not science fiction. It is in fact truth. You are all experiencing a force field right now, the Earth's gravitational field. But this unit is more about electric fields. The force field that surrounds a mass is a gravitational field. If you throw a ball into the air, it follows a curved path. Earlier chapters showed that it occurs because there is an interaction between the ball and the Earth, between their centers of gravity to be exact. Their centers of gravity are quite far apart, so this is action at a distance. Do you remember the picture of the Earth with the little spaceship way out here, right? That's not really very well drawn. Oh, let's make it a different color here. Let's see if I can make it more. Yeah? Okay, right? And it's interacting with the Earth's gravitational field. Do you remember what that gravitational field looks like? Remember this diagram?
That's a spaceship.
Yes, it's a poorly drawn spaceship. Kind of looks like a boot insert. You laughing at my drawing?
That's like the spaceship.
It's got a, yeah, it's,
You gotta draw a better one.
You're all like an alien.
Oh!
That looks like a nail.
okay, quick. Look at the side of the earth!
I could fit that.
Oh, now I got it all set. Anyways, there is, Nate, there is a gravitational force towards the center. Even though there is no rope, there's no chain, there's nothing able to pull that, right? It is that idea of action at a distance. And we say that the spacecraft is in contact or is interacting with the Earth's gravitational field. Same idea with electric fields. The idea that things not in contact could exert forces on one another, bodily, Isaac Newton, and many others. The concept of a force field eliminates the distance factor. Can you highlight that sentence for me? The one that I just said. Those of you still with earbuds in your ears should get them out. Okay, we're under electric fields, second paragraph, second sentence. The concept of a force field eliminates the distance factor. These famous scientists didn't like the fact that there could be a force applied to an object without there being some contact. Like, how do I use the force to drag that chair towards me? Okay? The idea of this force field eliminates that. The spacecraft is in touching the Earth's gravitational field. The ball is in contact with the field all the time. We can say the ball occurs because it interacts with the Earth's gravitational field. It's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the masses of the Earth and other astronomical bodies that are responsible for the field. Those of you that went and saw Matthew McConaughey, what was it? What's the name of that movie? What is it? Interstellar. Well, remember that they use the gravitational field of Jupiter, right, to slingshot them.
My mind. That's what they use the gravitational force to do.
Yes, they certainly did.
Wasn't Jupiter is like that huge planet thing that they found there, and there's a whole bunch of stuff going on now.
Whole bunch of stuff going on, yeah. Good analysis.
You didn't even know.
Just as the space around the Earth, it was pretty good. Nate, third paragraph. Just as the space around the Earth and every other mass is filled with a gravitational field, the space around every electric charge is filled with an electric field, a kind of aura that extends through space. In figure 33.2, focus. A gravitational force holds a satellite in orbit. And there's a picture in the bottom left-hand corner there. You can see the satellite orbiting the planet. An electrical force holds an electron in orbit about a proton. On the right-hand side, you can see the electron revolving, orbiting around the proton. In both cases, there is no contact between the objects, and the forces are, again, acting at a distance. And I'm emphasizing that because there's a question coming up that talks about action at a distance, and kids always say to me, I don't know what they're talking about. I'm talking about there being a force exerted at some distance without there being contact. Okay? But the object is in contact with the field. Now, does this field truly exist? If you put on special field glasses, can you see the lines? No. It's just a model. It's a scientific way of explaining, Nate, what's going on. Putting this in terms of the field concept, we can say that the orbiting satellite and the electron interact. Nate, follow along. Do you know where we are?
Third paragraph.
No. Oh, that is the third paragraph. Bottom of the third paragraph. Putting this in terms of the field concept, we can say that the orbiting satellite and electron interact with the force fields of the planet and the proton and are everywhere in contact with these fields. In other words, the force that one electric charge exerts on another can be described as the interaction between one charge and the electric field set up by the other. Now, flip the page, but let's not move on just yet. If we talk about the gravitational field between me and the chair is in my gravitational field, but I am also in the chair's gravitational field. Now, me and the chair are relatively the same size. We have a very small gravitational field, right? The spacecraft and the Earth. The Earth is ginormous compared to the spacecraft. Does the spacecraft have its own gravitational field? Yes, but it's infinitely small compared to the Earth's. Okay, same idea here. Yeah, when you have a big object, it has big gravity, right? If you have a big object with a large positive charge and a little teeny tiny electron way out here, which one has the bigger electric field? This one here, the big one, the bigger, more massive charge one, okay? Does this guy have an electric field? Yeah, but it's so tiny that it's practically not there. We don't worry about it. Okay, we're on page 2 now, the top of the page. An electric field has both magnitude and direction, which means it is a vector quantity. It doesn't say that, but that's what they're trying to say in roundabout terms. Electric fields are also vector quantities. Its magnitude or strength can be measured by its effect on charges located in the field. Imagine a small positive test charge, something that you use to test it out, that is placed in an electric field. Where the force is greatest on the test charge, the field is strongest. Where the force on the test charge is weak, the field is small. Basically, this thing right here. We've defined the electric field qualitatively as the region of space around a charge where a positive test charge experiences a force. Right? And the bigger force, we're defining the electric field quantitatively as a force per unit charge. The bigger the force, the bigger the charge. And vice versa. The bigger the charge, the bigger the force. The direction of the electric field at any point by convention, and you're going to highlight this, is the direction of the electrical force on a small positive test charge placed at that point. We always use a small positive test charge. Again, always the direction that a small positive test charge moves. Thus, if the charge that sets up the field is positive, the field points away from that charge. If the charge that sets up the field is negative, the field points toward it. In the right-hand side there, in that empty space, I want you to draw this picture. A big negative charge, and out here is my small positive test charge. What is the direction of the electric field? Towards no, negative is towards, yeah. And if the object creating the separate drawing, if it's a big giant positive charge, and out here I've got a little tiny, what's this guy out here? He's the positive test charge. Positive test charge. Which direction is the field? Which direction is the force? Away. And that's true in any space around it, right? Now, let's compare this to gravity. My spaceship is always interacted with gravity, is always towards or away from Earth. Always towards, right? Things fall to the Earth. Things never go flying away from the Earth. Gravity is always towards. There's only one way for it to go, towards, right? Things are attracted to the sun. Things are attracted to the moon. Things are attracted to me. Because I have such a gravitational personality. However, electric fields are different because there can be negative and there can be positive. Now, ironically enough, people that are positive tend to push people away. People that are negative tend to, it's kind of backwards to what you might expect.
Negative people push negative people away.
However, because of this dual nature, because of that positive negative charge thing, we have to decide, could I have said we're always going to use negative test charges? Absolutely. I could have said that. However, we would be going against worldwide convention. Could we say, starting tomorrow, green lights in Dauphin mean stop? We could. It'd be a bad idea. Right? Convention is red means stop, green means go. No one complains. How come we can't do it the other way? It's just the way it is. Same idea here. It is always a positive test charge. Always. So, towards negatives and away from positives. Got it? I just covered this one, and I've talked about this one, and we've started to talk about this one right here.
I guarantee you, the day we write the test, I'm not going to remember any of that.
Why is that, Lucas?
Because that's just the way my brain works. It filters all those.
Did you jot it down on the side there?
Yeah, I did.
Yeah.
How much theory is in this student?
This one actually has a little bit more theory than others, I'd say.
So always a positive test.
Always a positive test charge. If you get anything out of today, remember this. Always positive test charge.
That's all right now.
Okay. Now, at the bottom of that first paragraph there, imagine a small positive test charge that's placed in an electric field. Where the force is greatest on the test charge, the field is strongest. Where the force on the test charge is weak, the field is small. Now, with this diagram here, where would you expect the field to be strong? Closer. Where would you expect it to be weak? Farther away. Maybe we should add that on our diagram, right? Here it is. Strong the field is.
Strongest one.
Over here it is weak. Strong it is here. Weak the force is over there. It doesn't matter whether it's positive or negative. It makes no difference on the strength.
They look like the same distance.
They are. There, I meant them to be.
What the heck?
Where it is strong, the lines are close together, and where it is weak, the lines are farther apart. Do you remember that idea?
Oh, yes, sir.
Okay? Alright. Second paragraph. The direction of the electric field at any point by convention is the direction of the electrical force on a small positive test charge. Thus, if the charge that sets up the field is positive, the field points away. If the charge is negative, it points towards, like so. Be sure to distinguish between the hypothetical small test charge and the charge that sets up the field. In other words, do we worry that this guy's got a little bit of a field around him? No, he's so small that he's insignificant. Same thing with this one here. Now, in the footnote below that, the strength of an electric field is a measure of how great a force will be exerted on a small charge placed in the field. The test charge must be small enough so that it doesn't push the original charge around and thus alter the field we're trying to measure. If the test charge Q experiences the force F at some point in space, then the electric field E at that point is equal to the E is equal to the force divided by the charge. The electric field is how much force per unit of charge. Small q is charge. Small q is charge. Typically, when we're talking about the charge that's setting up the field, we will talk about big Q. Big Q stands for the charge on the object setting up the field. Small q refers to the smaller charge that's experiencing the force. Okay, this is analogous to the Earth, and this is analogous to the small spacecraft. Nate.
Do you remember that old movie where that asteroid circling towards the Earth? Like everyone's like getting ready for it. Like,
Oh, and then like.
Elijah Woods like gets married at like 15 or so. Yeah.
No, I
What's the
don't.
movie?
What's it called?
I don't.
How's he get married?
Okay, electric field lines. Now, I've already started to talk about this already, but let's sort of explain it a little bit more in depth. Electric field lines. Since an electric field has both magnitude and direction, it is a vector quantity and can represent it by vectors. The negatively charged particle in figure 33-3 top, that's the one over there on the right-hand side, is surrounded by vectors that point toward the particle. So you see, on the right-hand side right there, you see this picture. And you will notice all these little arrows. And as the arrows are close together, and I won't draw them all because I'm going to be there a while, do you see that they get smaller as they get farther away? Okay? Because it gets weaker. These, my friends, are vectors. Those are vectors, right? If the particle were positively charged, the vectors would point away. If the vectors always point in the direction you have noticed. The magnitude of the field is indicated by the length of the vectors. Because these are vectors, the strength of the field is represented by how long they are. But is there an electric field strength right there? Yeah. And is there one 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 right there? Yeah. And I could literally spend all day doing this, and what would I end up with? I would end up with nothing but blackness.
Black hole.
It'd be completely covered in vectors, and it would be utterly useless. That's why I'm not going to do it. Okay? And so, the electric field is greater when the vectors are long, longer when the vectors are short. To represent a complete electric field by vectors, you would have to show a vector at every point in the space around the charge. Such a diagram would be totally unreadable. It would be entirely black. It would be useless. A more useful way to describe an electric field is with electric field lines, which is what we just drew. Okay? Much like we had gravitational field lines. Not vectors. Not vectors. Do they look like vectors? Yes, they do, because they're arrows. Not vectors. Electric field lines. So, on this diagram here, on your page, the top one are vectors. The bottom one are electric field lines. How can you tell the difference?
One's all dotted, smaller.
Yeah, and they're all varying lengths, right?
Right.
The one at the bottom is they're all the same length. Does the length of the bottom one matter? No. What matters is how close they are to their neighbor, right? It's strong where the lines are close together. Again, not vectors. The length does not matter. Does that make sense? Yeah? It's how close they are together that matters. Now, is there an electric field right here? Yes, but I don't have to draw an arrow because it's not the length of the vector at that point. It's how close the lines are at that point. Okay, that's the difference. I know it's a technicality. It's kind of important. Okay, at the bottom of the page. And more useful way, electric field lines, where the lines are farther apart, the field is weaker. For an isolated charge, the lines extend to infinity. They do not end right there. They literally go on forever. And again, what matters is how close they are to their neighbor. And they get farther apart as you go wider. In fact, inverse square law. Twice as far, a quarter of the strength. While for two or more opposite charges, the lines emanate or start from the positive charge and terminate on a negative charge. Do you see this picture at the bottom? I'll have to draw it here.
Really weird looking one.
Well, do you see this one right here? Okay, so this is an electric field between 2 point charges, between positive and negative. How come the lines point towards the negative charge? Because if I put a positive test charge there, where would it go? Towards the negative, like so. Right? If I put that positive test charge anywhere there, it will go towards negative. And so the field lines always go from positive to negative. And I don't use the word always often because it's dangerous. Because it means always. Because it only takes one instance and always doesn't work anymore, right? But I'm telling you, always positive to negative. I think I've emphasized that enough. If you've got something like this, if you've got two electric plates, and this plate is positive, and this plate is negative. Which direction do the lines go?
Right.
From positive to negative. And, good question. What if they're both negative?
I feel like this, you know, like this bad.
Well,
They just go back and forth, wouldn't it?
It bounds.
There's just always one away.
if I take a positive test charge and put it here, what's it going to do? Well, it's going to go towards the one that is the stronger. So if it's sort of there, a little close to this guy, where's he going to go? He's going to go to there, right? If he's a little closer to this guy, he's going to go to there. If he's right in the middle, like a tug of war, probably just stay right there. Okay?
Oh, that's like when you put like a piece of like a magnet down a copper pipe. Would that be
Sort of, yeah. Sort of. That's a little different concept, but kind of. But imagine, if you will, this concept here. Didn't quite work out very good. I'll redraw it instead. What did our friend Millikan do? You remember? Remember, he put an oil droplet in the center with a positive charge and managed to get it floated or suspended, which would mean the top would have to be negative and the bottom would have to be positive, and the field lines would be like this, right? How come then, how did he manage to get it to flow? Like, couldn't the positive go like all the way up? What's the other force that's acting here? Gravity. The weight force. And when the weight force and the electric force were balanced, what does it do? And I'm going way farther ahead than I wanted to today, but that's fine. When the electric force is equal to the weight force, the net force is zero and it floats. Exactly. Suspended in air. And that's how Millikan came up with the charge Q. He got it to float, which is a way of figuring out what the actual charge was, and he actually managed to figure out what the charge on a single teeny tiny electron was.
How do you see that?
Really good eyes. You squint a lot. It's called a microscope. Does anyone know what the number that Millikan came up with was? Anybody remember? You're going to know it by the end of this unit. It's 1.6 times 10 to the minus 19. 1.6 times 10 to the minus 19. If you ever get that question on Jeopardy or Who Wants to Be a Millionaire and you've got phone a friend, I'm your guy. 1.6 times 10 to the minus 19. I'll take useless trivia for 200, please, Alex, and I'd like to phone Mr. Bennett.
When I'm writing the test, then can I call you?
Useless trivia, there we go.
Yeah.
I wouldn't even use you for that question. I just wanted you for any question, then I would like.
You know everything.
Thanks, man. I'll take that as a compliment. Okay, flip the page. Good question there, Mitch. Flip the page over. I'm almost done. Photographs of field patterns are shown in figure 33-5. These are actual pictures. The photographs show bits of thread that is suspended in an oil bath surrounded by charged conductors. The ends of the bits of the thread are charged by induction and tend to line up end to end with the field lines. So they're like iron filings in a magnetic field. They show the field lines. Notice that between the plates, the threads are aligned parallel to each other. That's in the bottom left-hand corner. See how the lines are like almost parallel? The field has a constant strength between the plates. Also notice the threads inside the cylinder are unaligned down here on the right-hand side. What does that tell you? There's no alignment in the bottom right-hand one, the inside. There's no electric field. No electric field inside. There's no electric field in the space inside a conductor. The conductor shields the space from the field outside. So, I would like to, let's just sort of try and come up with, you've got, okay, and we've got this kind of look, right? Oh, I better be careful not to draw arrowheads. Yeah. You kind of got this look on the top one. Can you tell me what the charges on those two round points are? Do you know which one is which?
Negative is the one up first.
How do you know?
Because it needs to be first.
Does it show that? On the picture here,
Well,
all you know is that one is positive and one is negative. It could be the other way around, right?
yes.
It could, we don't know, we can't tell. But we do know that they are opposite. What about the one on the right? What can you tell me?
Both negative.
Both the same. Either both negative, and you'll notice that they tend to do this. And Mitch, this sort of is the answer to the question that you were asking. They go away from each other. Okay? But they could be both positive as well. Just move these over here. Okay? So they both could be positive as well. We can't tell without arrowheads. This one down here, opposite charges, good. Right? How do we know? What would it look like if they were both positive? Yeah, it'd be kind of like this, right? That kind of thing? Does that make sense? And what would you say about the charges on the bottom right-hand corner there? Opposite, right? One of each. Very good. If you can identify that, that's another good thing as well. You're going to see questions like that, where I'm going to say, what are the charges on it, right? Or I'll ask you to draw them. There will be ones like that as well.
Why does one opposite?
Well, because you can see that it's going from one to the other, right? They're not being pushed away. There's no sort of repelling action. Flip the page over to the very last one. If our only concern for electrical forces were limited to isolated point charges, the electric field concept would be of limited use. The force between point charges is adequately described by Coulomb's law. Charges most often are spread out over a wide variety of surfaces. Charges also move. This motion is communicated to neighboring charges by changing the electric field that emanate at the speed of light. As later chapters will show, the electric field is a storehouse of energy. The energy can be transported over long distances by an electric field, which may be directed through and guided by metal wires or directed through empty space. That's how they transfer all that energy from northern Manitoba through the hydro wires. Okay, quick question on the right-hand side. Suppose that a beam of electrons is produced at one end of a glass tube and lights up a phosphorus screen on the inner surface of the other end. When the beam is straight, it produces a spot of light on the middle of the screen. If the beam passes through the electric field of a pair of oppositely charged plates, it is deflected, say, to the left. If the charge on the plates were reversed, in which direction would the deflection occur? Be the opposite. It'd be to the right. Who cares about stuff like that? Well, I used to be able to point to an object and say, everyone in the room should care because you all have in your home a beam of electrons produced at the end of a glass tube and lighting up a phosphorus screen. Everybody in this room had one at one time in their home. But some of you, probably most of you, don't have it anymore. I don't.
What?
I used to have one in my room. I don't have it anymore. Mr. Burnett still has one. It's not a level lamp. Good question. What's the one thing that people have in the last maybe, I'd say 8 years have started to get rid of, but you might have one, an old one in your basement, or grandma might still have one. Electron beam, glass tube, phosphorus screen. It's called TV.
I have a TV in my house.
Do you? Do you have a box TV, a CRT,
Yes.
cathode ray tube?
Yes.
So here's how it works. Here's the screen.
The screen goes out, right? Like
Yeah, here's you over here looking at it.
There's a high pitched sound.
Here's the electron beam. Okay? And the electrons are shot out like this. And if your TV is shot, what do you see? You see like a single dot in the middle there, right?
When it closes,
Sometimes when it's shut off, you would see that as well. Exactly. Especially on the older model TVs, right? So how the old TVs would work was there's an electric field in here, and these negatively charged electrons were affected by the electric field, and they would be deflected to the screen very rapidly, and it would go back and forth like this, really fast, and would make the picture. And then we'd go back to the start, to the top, and go again, right?
That's how you can play a duck hunt game.
That's how what?
You play a duck hunt game because the beams and stuff.
Yeah. And if you took a magnet to an old TV, what would happen? You'd mess it up because the magnetic field would also adjust that electron beam. Okay, so that was the whole idea behind the original TVs. LEDs and flat screens, that's something else. I don't know how that works. Okay, left-hand side, concept summary. You can read that for yourself to summarize. There are some review questions there. There are some think and explains on the right-hand side. I'm going to give you the next 28 minutes. If you choose to work on these, that's awesome. If you choose to spend another half an hour with your group looking up Milliken stuff and making arrangements for filming and all that, that's also great. What isn't great is if you just waste the next 28 minutes. Cheryl, you're not even talking.
You got the kind of talk.
Yeah. Yes, go.